Hello everybody. In this video we're gonna solve one more example on the case of homogeneous reaction or molecular diffusion accompanied with a homogeneous reaction. And this case is gonna be related to water treatment unit. So here we have this water treatment unit where water contains toxic materials. It's I think it's phenol if I remember correctly, and this wastewater stream is fed into this treatment unit where treatment is done by microorganisms that react with or consume the toxic material. And this tank is where the bio or microorganisms are available, and then the water leaves the water treatment unit with lower concentration of this toxic material. This I'm kind of giving you a summary of what's written here just to save some time. And the microorganisms are not dispersed in the whole volume that we have. It's immobilized in a biofilm, which is this thing. So it's a circular disc that is held with a shaft, and the biofilm is sticking to both sides of this disc. So it's this black line here is just an inert material that is acting as a support that is holding the film on both sides. This is a gelatinous material that is holding the microorganisms in place, and so that they stay in the same place, and that's what we call immobilized microorganisms. So this is what it says, that the biofilm degrades the harmful materials into harmless products, mainly carbon dioxide and water vapor, using the cells in the biofilm, which are the microorganisms. We can assume that this biofilm is a homogeneous material and the that we call B, and the toxic material is A. And we have here, if we consider this consumption as a reaction process, then we can consider this as the rate equation, which is the rate of consumption of A equals RA maximum multiplied by CA divided by KA plus CA. RA maximum is the maximum possible degradation rate of a species A, so this is the maximum degradation ever that you can get, and in the biofilm. And Ka is half saturation constant. It's just a reaction term that is part of the equation. It's not going to make a difference for us what these terms really mean. But this is what means or is important for us now, is this is the rate of reaction. And these discs that we mentioned are rotating discs, as it's mentioned here. So these rotating discs are they rotate to kind of agitate or make sure that the tank is well mixed. And this is a very important point here that we will discuss later, why it's important to keep in mind that this is well mixed contactor. So this shaft is rotating. They rotate exactly like the car wheels are rotating. You have a motion at the beginning of the shaft, which translates or transforms the motion to all the discs here. And by this we can tell that the concentration anywhere in this tank is the same. So this is the main part of it. And there is one other piece of information that we will discuss shortly. And the concentration, this is what it says: the concentration of a species A in the bulk fluid phase over the biofilm is constant if the fluid phase is well mixed. However, the concentration of A within the biofilm will decrease. This is the part that relates to mass transfer here. If you take a closer look at the biofilm, you will have this inert solid material, the impermeable material, where the biofilm is supported on. You have here the concentration of species A outside or at the surface is Ca node, and it decreases. There is this concentration profile where the concentration decreases due to the consumption of A due to or by the microorganisms. So what we need to do in this problem is to treat 0.1 meter cube per hour. So this is the flow rate of this whole stream. It's not the concentration, it's the whole flow rate, all the water with all the contaminants in it. It's 0.1 meter cube per hour, and the concentration of the toxic material is 0.1 gram mole per meter cube. So this is the concentration of the toxic material in water. And we know that this thickness delta, that we have it as delta here, is 2 millimeters. and we want to get the surface area of the biofilm that we need, the cross-sectional area of the biofilm that will be needed so that the concentration coming out of the of the unit is 0.02 gram mole per meter cube. So it enters at 0.1. We want to do 80% treatment, so 0.01 will come out as 0.02. This is 0.1, it's going to be here 0.02, so we remove 80% of the contaminants. And we know some data here. We know the value of, we have the value of Ka, we know the value of Ra, we know the diffusion coefficient of A and B, which is the toxic material in the biofilm. So I know all of this information. Before we start, we should know first one important information related to the information of having a well-mixed contactor. And this information is to understand it, this has to do with the kind of reaction engineering concept, which I'll cover quickly, which has to do with the well-mixed reactor, or sometimes we call it continuous stir tank reactors. I have discussed it in another video, I think in MATLAB, so you can go and check it if you are interested in more details. But the point that is important for us here is to understand what does this mean. So these kind of reactors are used for liquid phase reactions, where you have a feed which is a liquid and a product which is a liquid. And this tank is well mixed, so you have this agitator that rotates quickly and makes sure that the concentration everywhere is the same. So the assumption that we make in this kind of systems is that the volume of the reactor is very large compared to the flow rate of the feed. So the concentration that you have here is not going to make any big change or any significant change in the concentration inside. So it's like you have a swimming pool and you pour a cup of seawater in it. So the salt concentration is not going to be affected inside the swimming pool, because it's a huge swimming pool and small cup of water. So it's the same concept here. So it gets diluted once it enters inside. And this is the second part, that it's diluted once it's mixed. So the concentration all the time is not equal to the concentration inside. It's different, and the concentration coming out of the tank is equal to the concentration inside, because this is coming out of here, so it has the same concentration of the place where it originally came from. So this is the concentration. What we use here in any term that related to the process taking place inside the reactor equals to, I will use the concentration of the product. So this is the important part. This has to do with the concentration of the liquid that I use as a boundary condition in the biofilm, and this will be also valid for the reaction term that I am going to use for the KCA. So for the surface, the CA is CA out, it's not CA in. So I'm not going to use CA in anything related to mass transfer inside the reactor. So this is one important point to keep in mind. The second is to have a strategy of solution, because we want to get a concentration. I want to get an area, and this is the first time to deal with a problem where it's required to get an area. We always deal with problems where we want to get the concentration profile, we want to get the flux, we want to get the concentration at a specific point in the diffusing distance, but we didn't have this case before. So we need to understand how we can get this or relate this to our mass transfer concepts that we are dealing with. So the only equation or time that we talked about the area was the relation between the rate and the flux. So we know that the rate equals the flux multiplied by the area, because flux is rate divided by cross-sectional area. So this is the definition. So if I want to get the surface area, which is S, then I need to know both of these two. I need to know the flow rate of consumption, or the rate of consumption of A, and the flux of A. If I know these two, then and of course this is at Z equals 0, because this is where the flux starts. It gets consumed when it goes to the inside the biofilm. So I'm more interested in the flux at the surface. So this is the relation. If I know these two, then I'm good to go. Regarding the first part, which is the molar rate of consumption of A, then it's very simple to get from the information that we know. So you have concentration of 0.1 that's going inside the unit, and you have concentration of 0.02 that going outside the unit. So the difference between these two in case of steady state will not go anywhere except for the consumption. So the consumption is the difference between what's going in and what's going out. So so this is very simple logic. The molar rate of consumption of A, which is equal to the molar rate of A going in minus the molar rate of A coming out. And we can use the equations that we know, or the information that we know. I know the concentration, I know the flow rate, so the difference in concentration multiplied by the flow rate. This has units of gram mole per meter cube, this has unit of meter cube per hour, then the product will have units of gram mole per hour, which is the molar rate of consumption. It's 8 or 0.008 gram mole per hour. This is the first part. So I'm done with the first part of this equation, and then the NAS can be at z equals 0 can be calculated from 0.008 divided by the the surface area is going to be 0.008 divided by the n. So this is how we will have this strategy of solution. Why I need to get the flux, because this is the only way I can get the surface area, and why it's important, and how I can reach it. This is the mass transfer part in the problem. So we need to put our assumptions first so that we can apply them to the equations and simplify it as much as we can. So we have a constant source of A, which is the A in everywhere around the biofilm, which has uniform concentration, as we said, and A has a sink, which is the reaction which consumes A. So this is the steady state thing. The second point is that the concentration changes only in z direction, so it's only one-dimensional case, and that the biofilm is immobilized. We know that the film is stagnant, so we'll have diffusion in one direction. And there is one other point that I didn't write here, but this is kind of important. I think it doesn't need to be written already here, because it says it's dilute concentration of toxic organic solutes, and we know the concentration is 0.02 gram moles per meter cube. So you can imagine, if you have a meter cube, it will contain 0.02 gram moles, which is very, very, very small. So if you convert this into mole fraction, it's going to be very, very small value. It's kind of negligible value. So this is one other point that I didn't mention here, which is important to mention, because this is going to be part of the solution when we go through the solution. Now this is this part. Now A is consumed in the film where diffusion takes place. So I think this is very, very clear that it's a homogeneous reaction, and concentration of A is Ca node at z equals 0 for all biofilms, because we assume that it's a like perfectly mixing tank. So the concentration anywhere is constant, and we have constant temperature and pressure, which means that the diffusion coefficient is constant. So now when we want to start, we need to write our equations, which are the continuity equation and the flux equation. So the continuity equation will reduce to this form. It's one-dimensional. There is no unsteady state term. We have one-dimensional, so it's going to be d by dz. So it's very, very simple. And I know that the rate equation is takes this form. This is the form that we know. And we just put the negative sign because A is getting consumed, it's not produced. So this is the shape of the equation. There is one piece of information here that is important, that is kind of different from the textbook, and I changed it on purpose actually, which is the value of Ka. So we know that Ka is 30 gram moles per meter cube. That's what we have here, and the Ra is 0.57 gram moles per meter cube. One thing that's gonna be, or we're gonna mention in few seconds, is that the value of Ka is much more bigger than the value of Ca. So we can ignore the value of Ca compared to Ka. So the equation will reduce to a first order reaction. If you ignore this term, then it's gonna be R over K, which is kind of like the rate constant multiplied by Ca per 1. So it's for first order reaction. So this is one assumption that we'll make to simplify the solution for us. But actually, the original values that were in the textbook was 0.3, which is 100 times less, and 0.0057. So this was divided by 100, and this was divided by 100. So I believe that this values will not make this assumption valid. So if you have a value of Ka of 0.3 and the C is 0.02, then it doesn't make sense to ignore the 0.02 compared to the 0.3. So it's 0.3 and 0.32. It's kind of significant value or a significant difference in value. So it's not that small difference. However, if it's 30 and 30.02, it's kind of it's not that much big difference. So that's why I multiplied this and this both by 100, so that I keep the value of R divided by K constant. So I'm not changing the output of the equation or of the problem, but just want to make sure that the assumption is valid. So this is in case you check the textbook and find the different values. So I've done this on purpose. It's not a mistake. Anyway, so if you go back to the equation, if you assume that the K is much more, or if K is much larger than Ca, so this is the rate equation. And then if you substitute in the equation with the rate, then it's going to be dNA by dZ equals plus Ra maximum divided by Ka, Ca equals 0. And we know that this is the flux equation, and we have Xa is very small value because it's a diluted mixture. Then the flux equation is going to be just the first term, negative d dCA by dZ, which will look like this if I do the differentiation, and then the equation will take this form. So it's the second derivative of Ca with respect to Z minus R divided by dK multiplied by Ca equals 0, which we know has the general solution of this cosine and sine. So this is the general form of the solution. Okay, so now to solve this problem, we need to use boundary conditions to get the value of C1 and C2. And the boundary conditions that we know must be built on our understanding of the problem. So this is the equation again one more time. I will just put the square root because it's gonna repeat a lot. So I'm gonna put the square root equals to m. Just to make it like more simpler for us to write the equation instead of putting this bulky term inside. Now, when we see the boundary conditions, we know that one of the boundary conditions is very clear, is that the concentration is Ca out, which we know is 0.02 gram mole per meter cube. So I know Ca out. So this is one boundary condition, which is very simple, straightforward, which is Z equals 0, C equals C out. Now let's go to the second boundary condition, which some might think that it's like the problem that we solved previously, is that at this thickness Z equals delta, the concentration is 0. This might be right, but it's not guaranteed because I don't have any evidence that the concentration is 0. You might have a concentration that is larger than 0. But the boundary condition that I'm 100% sure of is that this is inert solid surface, which is impermeable surface. So it doesn't allow the diffusion of A to the other side. So this at this point the flux is 0, or I can say that the dCA by dZ equals 0 at Z equals delta. So this is the information that I'm pretty sure of, and we will check it later. So from the first boundary condition, it's gonna be exactly like the previous problem. So it's cosine is 1, the sine is 0, so it's gonna be Ca node equals C1. So I know that this is C1. For the second, I need to get the derivative so that I can put the derivative equals 0. So I'm gonna take the derivative, but I'm just used m instead of the square root. So it's Ca node multiplied by m, which is the derivative of this, multiplied by sine Zm plus C2m cosine Zm. I'm gonna substitute with the boundary condition information, so I'm gonna put delta instead of Z, and dCA by dZ equals 0. And from this I can get C2, which is negative Ca node tanh delta m. And from C2 from C2 and C1, I can substitute in the concentration profile equation, which is this, so I can get the shape of the concentration profile. And if I substitute with the C1 and C2 in this equation, I can get the dCA by the value of dCA by dZ, which will look like this. Okay, so this is how it looks like, either by differentiating this equation or directly substituting to this equation. It's going to be the same for both. Anyway, so this is the formula of the concentration profile. Now I can apply the equation at z equals 0 and use it to get the flux at z equals 0 when multiplied by negative d. So I now have the flux, and this is my ultimate goal, is to get the flux at z equals 0. And now I have the formula of the flux, and I have the almost everything. So I have R, D, K, A. So I know M equals whatever. I can calculate M. I have CA node, it's or CA out, which is 0.02. I know diffusion coefficient, so I know everything. So I can substitute. Now I can calculate M, and now I can calculate the flux by substituting with the data that I have or I know. And then from everything we have here, we can calculate N at Z equals 0. To be 3.9 multiplied by 10 to the minus 8, and finally calculate the surface area by using the formula that we mentioned in the strategy of solution, which is the rate divided by the flux, which is 0.008 divided by 3600s, because I want to make sure that units are homogeneous. So either to convert this from gram mole per hour to gram mole per second by dividing by 3600, or by converting the denominator into hour by multiplying the denominator by 3600. So they're both going to give the same result, which is 57 meters square. So this is the total surface area. It can be divided on 10 biofilms, on 20, on 100, whatever the areas that you have, or the unit areas that you have, but the sum of all the areas should be 57 meters square. So this is all what we need to do regarding this the problem. But there is one thing else that I want to check, which is take a look at the concentration profile, because I believe this is one interesting thing. I put it in the dimensionless form, where I have CA over CE node and Z dash, which is Z over delta, and we have this term which is our maximum delta square over dKA. They call it Thiele, and sometimes it's called Thiele modulus. So you can write the equation as C dash equals cosine phi, which is Thiele modulus, Z dash minus tan phi sine phi Z dash, which is almost the same parameter that we discussed previously. Anyway, so now when we take a look at the concentration profile, and this is an interesting thing, using the information that we have regarding the diffusion coefficient and the value of Thiele modulus will be almost 20, if I remember the number correctly. So the concentration profile will look like this, which means that the film is consuming the phenol within the first 40% of the whole length. So it's doing like a good job to take care or remove all the phenol in the first part, which is not bad, because it will give you some flexibility to operate the unit either for higher capacity or for cases where some of the cells are not active. So you'll have other backup cells that will do the job for them. So this is the first part. The second is to try to see how the profile looks like at different values of phi, because here you can say, okay, so now I have the profile showing that the concentration is 0 and at z equals delta. So if I put the concentration equals 0 at z equals delta, so I should be getting the same result. But this is true, but if you have different values of phi, it's not going to be the same result. So this is the profile in case of having different values of phi. So so you see here for phi equals 220. This 20 is our case. So for 200, if you have faster reaction, then this term, the concentration will decrease almost instantaneously and will get consumed in less than 10% of the whole length. And in our case it took us almost 30%. If you reduce the value of phi, it's gonna take 60 something, 70%. But then for phi equals 5 and for phi equals 1, you would see that the concentration is not 0. So the valid and the true boundary condition is that the flux is 0, but concentration can be non-zero value or a positive value. So this is what we see here. For small values of phi, it will have this concentration. And of course, in this case, you will find that the flux is less, which means that you need larger surface area to compensate the reduction in the flux. So this is kind of nice thing that to see, which in comparison to the other case is different in the previous case. In the previous problem, we said that Z equals delta, then concentration is 0, and we saw that all the curves ended up to be at 0 here. But in this case, we didn't have this boundary condition. That's why the profile was flexible to change the concentration on the other side. So that's all for this problem, and this is the last thing we will mention in chapter 24. So inshallah, in the next video we will start with the unsteady state molecular diffusion in chapter 25. So I'll see you then, inshallah. Goodbye.